Hey everyone, and welcome. Today we are diving deep into one of the most important and maybe one of the most misunderstood ideas in all of electricity: electric potential. You can think of it as this invisible landscape that tells every single charge where to go. And honestly, if you can grasp this, you're going to understand how so much of our world actually works. So let's get into it. Okay, here's the game plan. We're going to start with a really simple analogy for how electricity flows. Then we'll see how this whole concept of potential makes everything way easier. From there, we'll connect it to real-world energy, see how it dictates what happens inside conductors, and we'll wrap up by looking at capacitors, a device that is literally built around this one big idea.
All right, first up, let's try and take this abstract world of electricity and make it feel a little more, well, familiar, a little more intuitive.
I mean, think about it. We all just know that a ball at the top of a hill is going to roll to the bottom. It's just obvious, right? But what about an electron in a wire? What's the electrical version of a hill? What's telling it which way to go? Well, it turns out the answers to both of those questions are way more similar than you might think. See, with gravity, an object's path is all about the landscape. It moves from high potential energy down to low potential energy. Well, get this. Electricity has its own hidden landscape, and positive charges naturally roll downhill from a spot of high electrical height to a spot of low electrical height. This height, that's what we call electric potential.
So now let's see how this whole idea of electrical height gives us a much simpler way to describe what's going on in that electrical landscape.
You know, the old school way to describe forces on charges is by using something called the electric field, or the E field. Now, it's super powerful, don't get me wrong, but it's a vector field. That means at every single point in space, you have to define not just how strong the force is, but also which direction it's pointing. Imagine trying to map the wind by drawing a tiny arrow for every single speck of dust. It gets insanely complicated really fast. But here is the beautiful, elegant shortcut. This is the hero of our story right here. It turns out that whole complicated E-field vector can be completely described by a much simpler thing we call V. This equation shows the relationship. That little triangle is called a gradient, which is just a fancy math way of saying what's the direction and steepness of the fastest way downhill. This equation is our bridge from messy and complex to simple and elegant. And that V, that's our electric potential. So instead of a map with millions of arrows pointing every which way, we just get a map with simple numbers. It's like switching from that crazy wind map to a simple topographical map of a mountain. All you need to know is the elevation at each point, and you can figure out everything else because you know water is always going to roll downhill. It's so much easier. Okay, so if potential is this electrical height, what does that actually mean for things like energy and work in the real world? Let's connect those dots right now. This quote just nails it. It gives a really solid physical meaning to potential. The difference in potential between two spots isn't just some abstract number. It is, literally, how much work you'd have to do for every little bit of charge to push it from one point to the other against the flow, to push it uphill. And this wonderfully simple equation, W equals Q times V, is just the mathematical way of saying that. The work it takes to move a charge Q across a potential difference V is just their product. That's it. So you can think of potential as just potential energy, but divided by charge. It's a beautifully simple and incredibly powerful idea. And this finally brings us to the unit we all know and love, the volt. A volt isn't some weird, magical electrical thing. It's directly connected to energy. 1 volt literally means it takes 1 joule of work to move 1 coulomb of charge from one point to another. It's the bridge that connects our electrical landscape directly to the physics of energy. We can really see this idea of stored energy in action if we imagine building a system of charges from scratch. Okay, so the first charge you put down, that one's a freebie. It takes 0 work because there's no field to fight against. But then you bring in a second charge. Uh-oh, now you have to do work against the potential created by that first one. And the third one, you have to push it against the combined potential of the first two, and so on. The total energy you've stored in that final arrangement is just the sum of all the work you did step by step. Okay, the theory is great, but how does all this potential stuff actually play out in real materials that we use every day? Let's take a look at conductors. First, there's a key term we've got to know, equipotential. And it means exactly what it sounds like. It's a region or a surface where the potential is equal everywhere. So if our electrical landscape is a map of hills and valleys, an equipotential is like a perfectly flat, perfectly level plane. There's no downhill anywhere, so charges have no reason to roll. And here is the absolutely mind-blowing part. An ideal conductor, once it settles down, is an equipotential surface. The whole thing. Why? Because if it weren't, if there were any little hills or valleys inside, the charges are free to move, so they would move. They'd flow around until everything was perfectly level. And that one single fact explains everything else on this list. The electric field inside has to be zero, any extra charge has to live on the surface, and the E-field lines outside have to hit the surface at a perfect 90-degree angle. It all follows from that one idea. And this isn't just theory. This explains real-world magic like the Faraday cage. The metal shell of your car, for example, is a conductor. So during a thunderstorm, all that charge from the lightning strike arranges itself on the outer surface to make sure the entire car stays in equipotential. The result? The electric field inside is canceled out, keeping you, on the inside, perfectly safe. Pretty cool, right? All right, for our final topic, let's look at a device that was specifically engineered to take advantage of this whole potential difference idea, the capacitor. At its heart, a capacitor is dead simple. It's just two conductors with an insulator sandwiched between them. That's it. By pulling charge from one conductor and putting it on the other, we create that potential difference, V, between them. And it turns out that the ratio of how much charge we stored to the potential difference we created is a fixed number for that device. We call it capacitance. And the really key takeaway here is that capacitance is all about geometry. Just look at the formulas. It doesn't matter how much charge you put on it or what voltage you apply. The capacitance only depends on the physical stuff, the size of the plates, their shape, how far apart they are. It's purely a property of its construction. And this is where it all comes together. All that work we did to separate the charges, to drag them across that potential difference, that work isn't lost. It's now stored as potential energy in the capacitor. And the amount of energy you've stored is 1/2 times its capacitance times the square of the potential difference. We've successfully used potential to bottle up energy in a device. So we've gone all the way from a simple analogy about hills and valleys to a real formula for stored energy. But this whole classical theory leaves us with one fascinating, really deep puzzle. If you use these same equations to calculate the energy it would take to build a single point charge, like an electron, the answer you get is infinite. This tells us that somewhere, at the very smallest scales, the theory breaks down. It's a mystery that points us towards the even weirder world of quantum mechanics. So, what do you think is going on here? Where's the flaw?